Hello there, and welcome to Sleepy Traveler, where every distant light becomes a quiet story to fall into. I'm so glad you found this small pocket of calm in a universe that never stops humming. Beyond whatever walls surround you, the night is holding countless stars, some so near that we can almost think of them as neighbors, though they still live behind vast oceans of distance. Tonight, we'll trace the quiet paths we've already carved into that darkness, from the probe that skims close to our sun to the old travelers like Voyager and New Horizons, still drifting farther than any human has ever gone. From there, we'll lean softly into tomorrow's ideas, sails pushed by sunlight, engines warmed by nuclear heat, and subtle hints from quantum physics about how we might one day cross the spaces between stars. Nearby systems like Alpha Centauri, Sirius, and other faintly glowing homes may be waiting with worlds of their own. If this kind of gentle, starlit wandering feels right to you, a soft like and a quiet subscribe can help other sleepy explorers find their way here too. For now, we'll simply keep those distant suns in mind and let the journey unfold, one quiet thought at a time. We were born into an age where wandering beyond our own sky is no longer just a dream in old books. Silent machines have already slipped past the familiar paths of the planets, tracing long, pale arcs through the darkness. Dozens of probes have flown toward the far edges of our sun's family, and space telescopes now float in orbit, opening their mirrors like calm eyes that can see almost all of the visible universe. And yet, for all of this, it feels as if we are still very close to the shoreline. Within just a few dozen light years of Earth, there are thousands of other stars and planets waiting quietly for the day someone truly comes to visit. In this gentle stretch of imagined travel, we follow the paths humans have already drawn and the ones we still only whisper about. Our route begins very near home, but in a place that feels anything but safe, deep down in the bright gravity well of our own star, in a region where the light is so fierce it can strip matter apart. There, the Parker Solar Probe circles again and again, edging closer with each orbit to the restless ocean of hot, charged gas that surrounds the Sunday. From that blistering neighborhood, our thoughts will drift outward, crossing the solar system the way a slow camera pans across a wide landscape. Far from the sun's glow, we will catch up to the legendary travelers that left their homeworlds decades ago. Probes like Voyager and others that are now slipping onto paths that will never bring them back. Beyond them lie ideas that have not yet flown, but already live in engineers' drawings and physicists' notes. New kinds of engines that might push us beyond the orbit of the outermost planets, across several light years of interstellar space, toward the nearest stellar neighbors, such as the small system bound to the name Alpha Centauri. For more remote suns, the usual rockets and careful gravity assists may simply not be enough. This is where stranger concepts appear at the edge of our imagination, the kind that sit midway between solid science and speculative fiction. Among them is the idea of bending space-time itself, often called a warp drive, a mathematical construction that would not so much move a ship faster than light as reshape the space around it. Thoughts like these, wild but carefully written in equations, are what allow our imagination to keep going, to picture visits to stars dozens of light years away, scattered like cold lanterns across the dark. To understand why all of this effort keeps turning back to our own star, why a probe like Parker dares to graze the sun, It helps to sit for a moment with what the sun truly is. In November of the year 2021, Parker came closer to the sun than any probe before it. At one point, it was only about 8.5 million kilometers from the solar surface, skimming the outer atmosphere of the star. In that pass, it became the first human-made object to touch the sun's corona, that ghostly, shimmering outer layer that we usually only notice during a total solar eclipse. To reach that place, engineers had to solve problem after problem. How to shield instruments from heat that would melt most metals. How to fly through a region where charged particles move like a storm in every direction at once. It is natural to ask why we would go to such trouble, why we would send a fragile machine into a place where, if anything goes wrong, everything nearby might as well be ashes. The answer begins with the star we live beside. Our sun is a main sequence star, meaning it is in the long, steady middle chapter of its life. Its age is about 4.5 to 4.6 billion years, old enough that it has watched the solar system grow from dust into planets, but young enough that it still burns with a calm, reliable light. By its spectrum and size, astronomers place it in the class called G2V, a typical yellow dwarf in technical language, though there is something quietly misleading about the word dwarf here. From Earth, the sun looks like a small disk that you could hide behind a fingertip if you held your hand out at arm's length. In truth, it is enormous. Its diameter is about 1.4 million kilometers, roughly 109 times that of our planet. If the sun were the size of a large round doorway, the Earth would be about the size of a coin. Its mass is about 2 times 10 to the power of 30 kilograms, some 333,000 Earths worth of matter. Altogether, the sun accounts for about 99.9% of the total mass in the solar system. Everything else, the planets, their moons, asteroids, comets, is just a thin scattering of leftover crumbs. We are used to picturing the sun as a simple glowing ball, but it is a layered, dynamic object. Its visible surface, the part we see with our eyes through proper filters, has a temperature of about 5,800 Kelvin, or around 5,530 degrees Celsius. Even there, the temperature is not perfectly even. Some places are a little cooler and appear as darker smudges called sunspots. Others are slightly hotter. Deeper inside, the heat climbs to tens of millions of Kelvin. Strangely, far above the visible surface, in the corona, the temperature also vaults back up to values of 1,000,000 Kelvin or more. Those inner depths and that thin outer halo are both far hotter than the surface our eyes meet, and yet they contribute little to the light we see directly. The sun's brightness and warmth come from what it is made of and from what is happening in its heart. About 92% of its atoms are hydrogen, the simplest and lightest element in the universe. This gas is the main fuel for most stars. Under the immense pressure and heat in a star's core, hydrogen nuclei move so fast and collide so often that they can merge or fuse into helium. When that happens, a small portion of their mass is transformed into energy, as described by Einstein's famous relation between mass and energy. Helium, the next element in the periodic table, gradually gathers in the sun's center as this process continues. At the moment, helium makes up roughly 7% of the sun's volume and about a quarter of its mass. Mixed into the stellar material are also tiny fractions of heavier elements: carbon, oxygen, nitrogen, neon, and others. Together, all these metals, as astronomers call them, are just a trace, but they tell the story of earlier generations of stars that lived and died before the sun existed, enriching the gas from which our system formed. Inside, the sun is arranged in shells, each with its own way of behaving. At the very center lies the core, a compact region that takes up about 1/4 of the sun's total radius. There, the pressure is crushing, and the temperature reaches around 14 million Kelvin. A single cubic meter of material in the core can weigh on the order of 150 tons, as if a small hill were squeezed into the space of a desk. It is in this dense, blazing heart that thermonuclear reactions occur. Every second, roughly 4.26 million tons of matter are converted into energy in the form of light and other radiation. That continuous transformation is what keeps the sun shining and what ultimately warms the surface of Earth. Wrapping the core is what astronomers call the radiation zone, a thick layer that extends outward to about 70% of the sun's radius. In this region, the gas is still so dense that it does not churn freely like water in a pot. Instead, energy moves outward, mainly in the form of photons, particles of light. A photon born in the core does not travel straight to the surface like a clean beam from a flashlight. Instead, it wanders. It is absorbed by one charged particle, then re-emitted in a new direction, over and over, taking a path more like a drunk step through a very crowded room than a neat ray. Mathematical models suggest that a single quantum of light can spend anywhere from 10,000 to 170,000 years inside this tangled radiative maze before it finally reaches the next layer. During that long journey, the temperature falls from about 7 million Kelvin near the bottom of the radiation zone to around 2 million Kelvin near its top. It is a slow, patient process. Energy made in an instant in the core takes longer than all of recorded human history to climb toward the surface. Beyond this, in the sun's outer third or so, lies the convection zone. Here, the gas is cooler and less tightly packed, and it behaves in a more familiar way. Instead of passing energy outward mostly by light bouncing from particle to particle, this region moves heat by bulk motion, like the rolling boil in a pot of soup. Hotter plasma from deeper layers rises toward the surface, carrying energy upward. As it reaches the outer regions and radiates its heat away into space, it cools, becomes slightly denser, and sinks back down again. These giant convection cells, sometimes many tens of thousands of kilometers across, appear and disappear in cycles that last about 10 to 15 minutes near the surface. Seen up close, the sun's face would look a little like the surface of gently simmering water, each bright granule a place where hot plasma is rising, each darker edge a place where cooler material is sinking. This constant churning and the motion of charged particles within it help to create and maintain the sun's magnetic field, an invisible structure that threads through the solar interior and stretches outward through the entire inner solar system. That field shapes the solar wind and carves out a protective bubble around our star and its planets, a bubble we call the heliosphere. Above the boiling motions of the convection zone, the sun has a kind of atmosphere, built-in layers that grow thinner and more transparent with height. The lowest of these layers is called the photosphere. This is the region that emits most of the visible light we see. When you look safely, through proper filters, at the sun, what your eyes are really seeing is the photosphere. It is not very thick by cosmic standards, only about 100 to 400 kilometers deep. Across that distance, the temperature drops from roughly 6,600 Kelvin at the bottom to about 4,400 Kelvin near the top. or from a little over 6,300 degrees Celsius down to around 4,130 degrees Celsius. Above the photosphere lies a more rarefied layer known as the chromosphere, about 2,000 kilometers thick. Most of the time, its faint glow is washed out by the brilliant photosphere beneath, so from Earth, it is difficult to see directly. It becomes visible during a total solar eclipse, when the moon blocks the glaring disk, or through special instruments that isolate particular wavelengths of light. The chromosphere is surprisingly hot, with temperatures climbing from about 4,000 Kelvin in its lower parts to around 20,000 Kelvin higher up. Along its outer boundary, thin jets of gas called spicules are constantly shooting upward, like transparent grass blades made of fire, rising 5,000 to 10,000 kilometers above the solar surface before fading. Still higher out is the sun's outermost atmosphere, the corona. During a total eclipse, it appears as a pale, feathery halo stretching far into space. The corona is made of extremely thin, hot plasma shaped into loops, arcs, and streamers by the sun's magnetic field. Within it, one can find towering prominences, arches of glowing gas that can rise hundreds of thousands of kilometers above the surface, along with sudden flares and larger eruptions that hurl matter outward. Some of these features can reach scales of about 1 million kilometers. Despite its low density, the coronal gas is incredibly hot, with average temperatures between about 1 million and 2 million Kelvin, and in some active regions, peaks reaching around 20 million Kelvin. It is this outer region, the pale, fiery crown of the sun, that the Parker Solar Probe now sometimes crosses. Each close pass lets the spacecraft slip a little deeper into that bright, thinned-out abyss, moving through a place where the light is not just something to see, but something that can strip atoms bare. When scientists add up the energy flowing outward from the photosphere, the visible surface, they find something puzzling. The numbers suggest that the light and heat leaving that layer are not enough to raise the chromosphere and the corona to the astonishing temperatures we measure there. The farther you go from the surface, the thinner the gas becomes, and yet the temperature climbs again into the millions of Kelvin. It is as if you walked away from a campfire and somehow found the air getting hotter instead of cooler. That mismatch is a quiet sign that something is missing in our picture. This strange behavior is often called the coronal heating problem, a reminder that our tidy understanding of the sun still has gaps, somewhere in the dim space between what we can calculate and what we actually observe. Extra energy is being poured into the upper layers. Several ideas have been offered to explain it. According to one family of hypotheses, the chromosphere and the corona are warmed by waves in the sun's magnetic field. Those waves move through the plasma like ripples in a taut string, carrying energy upward and then breaking or dissipating into heat. Another idea leans on the acceleration of charged particles in the sun's strong magnetic field. In that view, particles are whipped to higher speeds by changing magnetic structures and then share their energy with the surrounding gas, raising its temperature. The Parker Solar Probe was built as a kind of quiet detective for these mysteries, designed from the start to slip into the sun's atmosphere and ask it questions firsthand. Its main purpose is to study the hidden processes in the upper layers of the solar atmosphere, where hot plasma, radiation, and magnetic fields all tangle together. The mission itself carries the name Parker Solar Probe, an honor to a physicist whose work helped shape our understanding of the solar wind. The project was approved years before launch, but the spacecraft finally rose from Earth On the 12th of August, 2018, it left our planet on a path that was never meant to bring it home again. A one-way journey inward toward the star that made us. Reaching its planned orbit was not a simple, straight fall. To come close enough to be useful, Parker had to perform a series of careful swings around Venus. Each flyby used the planet's gravity as a gentle hand on the probe's trajectory, changing its speed and angle so that the closest point to the Sun, its perihelion, drew nearer and nearer with every loop. All along, the spacecraft had to be ready for conditions that hardly resemble the emptiness we imagine when we picture space. Parker carries a thick heat shield, a kind of artificial shadow that always faces the Sunday. Behind that shield, the instruments sit tucked into relative coolness, even as the sun-facing side of the shield bakes. Every piece of hardware, every wire and sensor was chosen with those extremes in mind. The orbit is also designed so that the probe spends only a short time skimming the sun's immediate surroundings on each pass, then swings back out to cooler distances where it can radiate away some of the stored heat before diving in again. The core tasks entrusted to Parker are gentle in description but demanding in practice. The probe must measure the structure and behavior of the sun's magnetic field very close to its source, watching how it twists, stretches, and reconnects. It needs to sample the flow of energy streaming out from the star, to catch and weigh particles of the solar wind, and to record wave-like motions in the plasma of the corona. All of these data are pieces of the puzzle that might explain why those outer layers burn so hot and how the solar wind is launched into interplanetary space. Along the way, the spacecraft has also turned its cameras and detectors toward other sites. As it drifted inward through the inner solar system, it captured images of Venus, the planet that helps shape its path, and later of the bright visitor comet Neowise. These side glances are like notes in the margin of a much larger study, small gifts carried along on the way to the main work. To carry out its mission, Parker is equipped with a broad set of instruments. There are cameras that can see not just visible light, but also faint structures in the surrounding corona. There are particle detectors that catch protons, electrons, and heavier ions streaming past. Magnetometers measure the strength and direction of the magnetic field. Other sensors listen for radio waves and track radiation levels. Together, these devices give the probe something like a sense of touch and hearing in a place where no human body could survive. The environment they must endure is harsh in ways that are easy to underestimate. In addition to the intense heat on the sun-facing side of the shield, the instruments are bathed in a powerful stream of ionizing radiation. The sun's activity also fills nearby space with noise in radio and microwave frequencies, the very bands we often use to talk to our spacecraft. Sending a clear signal back to Earth from so close to the sun is like whispering across a crowded, echoing hall. Engineers must carefully time and tune the downlinks, choosing moments and frequencies that let the probe's voice rise above the solar roar. Despite these difficulties, Parker continues to loop around the sun, tightening its spirals like a moth in a complex dance around a lantern. With each completed orbit, its closest approach shrinks. In late February of the year 2022, it passed through the sun's corona once more, gathering a fresh collection of measurements. Plans and calculations show that by 2024, the probe's perihelion distance will be reduced to about 6.2 million kilometers above the solar surface, closer than any mission before it. At that point, the spacecraft's heat shield is expected to face temperatures of around 1,370 degrees Celsius. that is roughly 3 times hotter than the sunlit side of Mercury and only a little cooler than the melting point of iron. Even now, during close passes, Parker travels at remarkable speeds. Near perihelion, its velocity already reaches about 163 kilometers per second. Later in the mission, it is expected to accelerate to around 200 kilometers per second, making it the fastest human-made object ever flown, a small craft streaking through space faster than any bullet. A journey like this cannot last forever. Once Parker reaches its closest possible orbit around the Sun, it is expected to complete several more loops over the course of roughly a year. Each pass will drain it a little more. The spacecraft will gradually lose speed through subtle interactions and will endure cycle after cycle of extreme heating and intense radiation. Over time, the sensitive instruments will fail, one by one. Eventually, shield and structure alike will no longer be able to protect what remains, and the probe will drift inward, surrendering itself to the Sun's outer layers. In the end, it will be swallowed by the deep, bright sea of plasma it was sent to study. Yet before that quiet ending, Parker will have sent home a treasure of information. Detailed profiles of the solar wind, maps of magnetic fields, hints about the hidden engines that heat the corona. Those streams of numbers, turned into understanding, will become another small step in our slow exploration of space, a reminder that even brief, fragile missions can deepen our connection to the star we orbit. Far away from this dangerous closeness, another spacecraft has been making a different kind of journey, one that leads outward into the cold and the dark. New Horizons left Earth much earlier, on the 19th of January, 2006. By now, its distance from home is measured in tens of astronomical units, around 52 times the average distance between Earth and the Sunday. It moves through the outer solar system at a speed of about 14 kilometers per second, covering roughly 3 astronomical units each year, a steady, patient glide away from the light. New Horizons was built with a clear main goal: to visit Pluto and its large moon Charon, worlds that had long been little more than blurred points in even our best telescopes. Like many interplanetary probes, it did not go there in a straight line. Early in its voyage, the spacecraft flew past Jupiter for a gravity assist. The giant planet's pull bent and sped up its path, giving New Horizons an extra push toward the distant Kuiper Belt. During that close pass, the probe's cameras and instruments took advantage of the opportunity. They captured detailed images of Jupiter's swirling atmosphere and its family of moons. One of the most striking observations was the first video sequence of an erupting volcano on Io, Jupiter's highly active, lava-covered satellite. After this boost, New Horizons traveled on through the cold outer reaches, aimed squarely at its main target. It reached the neighborhood of Pluto in January of 2015. For a short while, as it swept past at high speed, the spacecraft became our stand-in eyes and hands in that remote environment. Its tasks were many: to photograph and map the surfaces of Pluto and Charon, to trace their craters, mountains, plains, and possible ice flows, to measure the strength of any magnetic fields and the behavior of the solar wind in that far-off region, to study their thin atmospheres and the way sunlight reflects from their surfaces. The mission plan also asked New Horizons to look for any small moons that might still be undiscovered, circling Pluto in faint, dark orbits, and to refine our knowledge of Pluto's path around the Sun by timing and tracking its position with great care. Each of these activities turned distant points of light into places with weather, structure, and history. When the main goals at Pluto and Charon were achieved, the spacecraft did not simply fall silent. It was still healthy, still powered by its radioisotope generator, still able to listen and respond. So it continued outward, crossing Pluto's orbit and entering more deeply into the Kuiper Belt, the broad ring of icy bodies that encircles the outer solar system. There, New Horizons used its cameras to study other objects, such as the distant worlds known as Quaoar and Arrokoth. From its unique vantage point, the probe also helped refine measurements of distance to nearby stars like Proxima Centauri and Wolf 359, using small shifts in their apparent positions against the more distant background. The power source on board New Horizons is not endless. Its radioisotope generator slowly produces less and less electricity as the years go by. Around the year 2026, the available power is expected to drop to the point where not all instruments can remain active at once. One by one, the most energy-hungry systems will be switched off, and the spacecraft's voice will grow quieter. Eventually, the last working detectors will shut down as well. When that day comes, New Horizons will still be out there, a small, silent craft moving through the dark at 14 kilometers per second, carrying the memory of what it has seen as it continues on its way. Far beyond Pluto's faint path, New Horizons keep sliding outward into a region where the sun is no longer a bright disk, but a sharp star among many. Each year, the distance between the spacecraft and the sun grows by several astronomical units, like a slow, steady heartbeat measured in orbits instead of seconds. If its journey continues as planned, then by around the year 2038, the probe will be roughly 100 astronomical units from the Sunday. At that distance, light from our star will take more than 13 hours to reach it, and the warmth that once powered the solar system's birth will feel like a memory. By that time, the radioisotope generator on board New Horizons is expected to have faded completely. With no electrical power left, its instruments will fall silent, one after another, and its transmitter will no longer be able to whisper across the dark. Any hope of two-way conversation will be gone. The craft will not stop, though. Its path is a hyperbola, an open curve that does not loop back. Following that trajectory, New Horizons will slip over the subtle edge of the solar system and never return, becoming one more small, quiet visitor to interstellar space. It will not be the first of our machines to do this. Long before New Horizons, two other spacecraft took on a similar fate. They were called Pioneer 10 and Pioneer 11, and they were among the earliest automatic probes we sent on journeys that would ultimately carry them beyond the reach of the sun's gravity. In a way, they were our first real messages in a bottle, tossed deliberately into the deep ocean between the stars. Pioneer 10 left Earth on the 3rd of March, 1972. Its main goal was to reach and study Jupiter, the largest of the planets. It took about 641 days, nearly 2 Earth years, for the spacecraft to cross the space between the inner system and Jupiter's orbit. On the 4th of December, 1973, Pioneer 10 arrived in the giant planet's realm. During its flyby, it sent back images of Jupiter's swirling cloud tops and its largest moons, turning what had once been fuzzy disks in telescopes into detailed worlds with bands, storms, and shadows. Its instruments measured the composition of Jupiter's atmosphere and probed the strength and shape of the planet's magnetic field. One especially important result was the discovery that Jupiter radiates about 2.5 times as much heat as it receives from the Sunday. That meant the giant planet carries its own internal furnace, powered by processes deep inside, and it helped scientists understand that gas giants are not just oversized versions of Earth, but a different class of world altogether. The data from Pioneer 10 became a foundation for our picture of how such planets and their moons behave. After its close encounter, Pioneer 10 did not turn around. It followed a path that would eventually carry it out of the solar system altogether. Its twin, Pioneer 11, took a slightly different route. This second probe also flew past Jupiter, using the planet's gravity to bend its trajectory, but its primary target was Saturn, the other great gas giant of our system. As Pioneer 11 passed through Saturn's domain, its instruments measured the strength of the planet's magnetic field and sampled the charged particles trapped within it. The cameras on board captured images not just of Saturn's striped atmosphere and its graceful rings, but also of two of its moons, Titan, with its thick, hazy envelope, and the smaller, icy Mimas. These early portraits revealed a system richer and more varied than many had expected. After finishing their main tasks, both Pioneer spacecraft kept going, drifting farther and farther from the Sunday. Estimates suggest that Pioneer 11 is now around 106 astronomical units from the center of our system, while Pioneer 10 has traveled even farther. But distance is not the only barrier between us. Their power sources weakened, their transmitters grew faint, and eventually their voices faded into the background. The last clear signal from Pioneer 11 was received in 1995, and the last from Pioneer, 10 inches, 2003. Since then, both have been beyond the practical reach of our antennas. Somewhere out there, they continue to move, small metal shapes gliding through a darkness that grows thinner but never ends. They are likely already beyond the regions we usually count as part of the solar system, yet they are still far behind two younger and faster travelers, Voyager 1 and Voyager 2. Launched later, but on more energetic paths, the Voyagers gradually outpaced the Pioneers and pulled ahead into the deep. Voyager 1 left Earth on the 5th of September, 1977. Its main mission was to fly past Jupiter and Saturn, taking advantage of a rare alignment of the outer planets. The spacecraft travels at about 17 kilometers every second, which adds up to roughly 3.6 astronomical units per year. That speed has carried it to a current distance of over 150 astronomical units from Earth, making it the most distant human-made object from home. The contribution of Voyager 1 to our understanding of the solar system is hard to overstate. As it swept past Jupiter, its cameras discovered previously unknown moons and revealed that the planet has a faint ring system of its own, a delicate band of dust encircling the giant. The probe recorded erupting volcanoes on Io, the innermost of Jupiter's large moons, showing that this strange world is the most volcanically active body we have yet found. The images and data gave solid support to the idea that Jupiter's Great Red Spot is not a fixed mark or stain, but an enormous storm, a swirling, long-lived hurricane larger than Earth itself. Voyager 1 went on to Saturn, adding to our knowledge of that planet's rings and moons before its path took it away from the plane in which most planets orbit. After its encounters with the gas giants, the spacecraft crossed the orbit of Neptune. Even though it never flew directly past that planet, its instruments continued to gather measurements about the environment at the edge of the solar system, recording changes in charged particles and magnetic fields as it approached the boundary where the solar wind meets the material between the stars. Over time, Voyager 1 left the Kuiper Belt behind, the wide, icy ring beyond Neptune, and moved into a region of scattered, distant objects. More importantly, it crossed the heliopause, the outer edge of the heliosphere. The heliosphere is like a vast bubble of influence blown by the sun, filled with solar wind, charged particles streaming outward. At the heliopause, the pressure of that outflow and the pressure of the thin interstellar gas balance. There, the wind from our star slows and is pushed back by the surroundings, and the magnetic field of the galaxy begins to dominate. For the first time, a working spacecraft found itself in the space between stars, not just in the sun's personal cocoon. Studying this region gives scientists insights into how stellar winds carve out protective cavities, how cosmic rays are filtered, and how our own system fits into the wider flow of the galaxy. Yet even this careful listening cannot continue indefinitely. Voyager 1 is powered by radioisotope thermoelectric generators, devices that convert the heat from radioactive decay into electricity. As the material inside them ages, the power available to the spacecraft slowly decreases. By around the middle of the decade of the 2020s, the generators are expected to produce too little energy to run the instruments and the transmitter together. Bit by bit, systems are being shut down to stretch the mission, but eventually, the spacecraft will no longer be able to send back data. The last signal will fade, and Voyager 1 will become another silent wanderer. Its journey, however, will go on in a different sense. Calculations suggest that in roughly 300 years, Voyager 1 will reach the inner boundary of the region we call the Oort cloud, a vast, hypothetical shell of icy bodies surrounding the solar system at great distances. Passing through this cloud, even at its high speed, will take an enormous span of time, on the order of 30,000 years. Only after that will it truly emerge beyond the furthest comets that still belong to our sun's family. About 10,000 years after leaving the Oort cloud behind, the probe is expected to pass within about 1.6 light-years of a star known as Gliese 445. It will not stop there. It will simply drift past, unnoticed by any local world, and continue its slow glide into the galaxy's depths. When we think of Voyager 1, it is natural to think also of its twin, Voyager 2, launched a little earlier. On the 20th of August, 1977, Voyager 2 followed a slightly different path, designed to take advantage of what was called the Grand Tour alignment of the outer planets. Its planned route included flybys of Jupiter, Saturn, Uranus, and Neptune. Along the way, it also used Jupiter for a gravity assist, passing close enough to feel the pull of the giant and borrow some of its orbital energy, turning that into extra speed and a new trajectory. At Jupiter, Voyager 2's cameras and instruments reinforced and extended the discoveries made by Voyager 1, adding more details about the planet's atmosphere, its storm systems, and its retinue of moons. Some of the images and measurements hinted at the possibility of subsurface oceans on Ganymede and Europa, icy moons whose cracked surfaces and magnetic signatures suggest liquid water may lie hidden beneath their frozen crusts. Later, at Saturn, Voyager 2 measured the temperature and the magnetic field of the gas giant, discovered several previously unknown moons, and sent back a great many images of the planet's rings and cloud tops. After Saturn, the path of Voyager 2 carried it on toward Uranus and Neptune, making it the only spacecraft so far to have visited these two distant ice giants. The flybys revealed tilted magnetic fields, complex atmospheres, and ring systems around both worlds. Dim, dark rings that had gone unnoticed from Earth. In total, the encounters with Uranus and Neptune led to the discovery of 17 new moons between the two planets. Passing near Neptune, the spacecraft felt the planet's gravity tug at its path once again. This close approach bent Voyager 2's trajectory out of the ecliptic plane, tipping it away from the flat disk where most planets circle. That change in direction meant Voyager 2 would not be able to visit any additional major planets, but it also set the stage for a different kind of work. Like its twin, it could now serve as a probe of the outer heliosphere and beyond, sampling the interstellar plasma and the cosmic wind that fills the galaxy. It helps measure distances to nearby stars through tiny shifts in their apparent positions, and it continues to map the structure of the heliosphere from a different angle than Voyager 1. At present, Voyager 2 is about 128 astronomical units from the center of the solar system, and the gap grows larger every second. Its speed carries it outward by more than 15 kilometers each second, a quiet, relentless escape that will eventually lead it, too, into the realm of the Oort cloud and beyond. If all goes as predicted, in roughly 42,000 years, the spacecraft will pass near a dim red dwarf star called Ross 248 in the constellation Andromeda. By then, whatever traces of our current world remain here will have changed many times over, but Voyager 2 will still be moving through the dark, a small reminder that once, long ago, a young civilization began to reach for the nearest stars. If its path unfolds as the calculations suggest, the closest Voyager 2 will ever come to Ross 248 will be about 1.7 light-years. That is still a vast separation, more than enough room to hide whole unseen systems in between. Much farther down its timeline, perhaps 300,000 years after leaving Earth, the spacecraft is expected to drift past Sirius at a distance of about 4.3 light-years. By then, our languages, our maps, even our continents may have changed beyond recognition, but Voyager 2 will simply glide through that distant neighborhood, almost certainly unnoticed. From here, there is no hope of picking out such a tiny, dark object against the starlight. It is effectively invisible, a grain of dust lost in a cathedral of night. Compared to those immense stretches, our own solar system suddenly feels more intimate. Of all the planets circling our sun, Mars is the one that seems to lean toward us most invitingly. Its orbit brings it into relatively close approach to Earth on a regular rhythm. At the most favorable times, the distance between our two worlds shrinks to just under 56 million kilometers. For light and radio waves, that gap is almost nothing. Signals can cross it in roughly 3 minutes. For a spacecraft, though, the story is very different. A journey between planets is not a straight line. Spacecraft must follow carefully planned curves, shaped by the sun's pull and by the gravity of other worlds along the way. To save fuel, they often use gravity assist maneuvers, swinging past planets to borrow a little of their orbital motion. The Perseverance rover, for example, traveled from Earth to Mars in a little less than 7 months. It rode inside a protective shell, gently adjusting its path as it coasted through the inner solar system before finally dropping into the thin Martian atmosphere. Future vehicles, such as the Starship design from SpaceX, are expected to cut that travel time, perhaps making the trip noticeably quicker, especially for missions carrying people. But for now, the exact durations for regular crewed expeditions to Mars remain a matter of estimates and simulations rather than proven schedules. Even with our best rockets and careful planning, hopping between these two neighboring planets takes many months of patient flight. When we lift our eyes from Mars to the stars beyond, the difficulty rises by more than a simple step. Traveling to other suns is a much more demanding challenge. Even light, which moves at just under 300,000 kilometers every second, needs more than 4 years to reach Proxima Centauri, the closest star to us beyond our own system. If we imagine taking our fastest existing spacecraft on that route, the time stretches out almost beyond intuition. Rough estimates suggest it would take around 4,000 years to make the same journey, and even that number is still optimistic. Part of the problem is the deep, gentle grip of the sun's gravity. To break free from that pull and head truly outward, a spacecraft must reach speeds of more than 47 kilometers per second relative to the Sunday. Achieving such speeds through rockets alone demands immense amounts of fuel, or a chain of gravity assists carefully threaded through the orbits of planets. Each of these assists takes time and depends on precise planetary alignments. Hopes for pushing much beyond those speeds with current chemical engines drift close to the border between realistic planning and quiet fantasy. The fastest probe we have sent so far is the Parker Solar Probe, launched by NASA in 2018. By using multiple close passes by Venus and diving very near the Sun, Parker has already reached speeds of around 147 kilometers per second, and future passes are expected to push that up to nearly 194 kilometers per second. That is roughly 700,000 kilometers per hour, a number that feels almost unreal compared to everyday experience. Yet there is a twist. Parker is diving inward, using the sun's gravity to gain speed, not trying to escape outward into interstellar space. Its trajectory cannot turn that incredible velocity into an easy road to the stars. Most spacecraft never approach such numbers. Many of the probes that explore our solar system travel at speeds closer to 11 kilometers per second once they leave Earth's immediate neighborhood. That is enough to enter orbit, to reach the moon, and, with patience and careful planning, to cruise toward other planets. But it also means that missions to the outer reaches toward Jupiter, Saturn, and beyond take years or decades to complete. The slowness is not from a lack of will, but from the nature of the engines we use. Chemical rockets, the kind that burn fuel and exhaust hot gases, have deep limitations. When you look at a tall launch vehicle on a pad, most of what you see is not payload, but propellant and the structure needed to hold it. The useful cargo, the spacecraft, the instruments, the habitat for astronauts makes up only a small fraction of the total mass. Engineers describe the efficiency of a rocket engine with a quantity called specific impulse, which is essentially a measure of how much push you can get from a given amount of propellant. For traditional chemical engines, we have already come close to the practical ceiling. Small improvements are still possible, but no sudden leap that would turn interstellar travel into a quick errand. So if we dream of crossing the gulfs between stars, we are almost forced to look for new ways of moving. Some of these ideas sound like fragments from a novel. Others are already quietly shaping the satellites that circle above us now. One family of engines giving us a taste of the future involves ion thrusters. Instead of burning fuel in a roaring flame, these devices take a gas, strip electrons from its atoms, and use electric fields to accelerate the resulting ions out of the back of the spacecraft. Each ion is tiny, but it leaves at very high speed, and in doing so, it gives a small kick to the spacecraft in the opposite direction. Ion thrusters have performance that can be tens of times better than chemical rockets in terms of specific impulse. In simple terms, they can squeeze much more push out of each kilogram of propellant. That means a spacecraft using them can either carry a greater scientific payload for the same amount of fuel or travel farther on a given fuel supply. The trade-off is that the thrust they produce at any moment is very small. They cannot lift a heavy rocket off Earth's surface. Their push is more like the steady pressure of a breeze than the jolt of an explosion. But in the vacuum of space, where there is no air resistance and no friction, even a gentle, constant push can gradually build up impressive speeds. These thrusters are not just concepts on paper. Since the 1970s, they have been used on satellites and some deep space missions for fine maneuvers, adjusting orbits, correcting trajectories, keeping spacecraft balanced in their paths. Quietly, they have become one of the tools that let modern probes stay on station for years with very little fuel. Still, for a true starship that must accelerate hard and fast for long periods, ion engines alone are not yet enough. Another way to think of propulsion is to step away from the idea of throwing mass out of a nozzle at all. Instead, one can imagine letting light itself do the pushing. Photons, the particles of light, have no rest mass, but they carry momentum. When they bounce off a reflective surface, they impart a tiny nudge. A solar sail is built to catch that faint pressure. It is essentially a very large, very thin mirror or shiny film, unfurled in space and angled to catch the flow of sunlight. Over time, the constant pressure of photons can gradually accelerate a spacecraft to high speeds, potentially hundreds of kilometers per second, without the ship carrying large tanks of propellant. There is a related idea called an electric sail, which uses the charged particles of the solar wind instead of light. Long, charged wires or structures extend from the spacecraft, interacting with the stream of ions and electrons flowing outward from the sundae. That interaction creates a kind of drag or push that can be tilted into a forward thrust. Both approaches promise very efficient propulsion in terms of fuel. The engine is, in a sense, the star itself. These sails have their own limits, though. They cannot help a spacecraft rise from the surface of Earth or any other planet. A separate rocket must first carry the craft into space, where the sail can then be deployed like a delicate, shimmering flower. And the farther a sail gets from a star, the weaker its push becomes. The intensity of sunlight and solar wind drops sharply with distance. So in the deep void between stars, these systems grow sluggish. Moreover, the sail material must be both extremely light and incredibly strong, able to withstand micrometeorite hits, radiation, and the mechanical stress of deployment. Some scientists and engineers imagine future sails made of graphene films or other advanced materials not yet commonplace, whisper-thin and tough enough to spread over areas many kilometers wide. Looking even further ahead, people have sketched designs for photon-powered starships, driven not just by natural sunlight, but by artificial beams. In these concepts, a powerful light source, perhaps a vast array of lasers, would shine onto a large reflective surface, such as a parabolic mirror or sail attached to the spacecraft. The constant flood of photons would push the ship to a significant fraction of light speed. A small quantity of antimatter has even been proposed as a way to power such an intense beam, since matter-antimatter reactions release incredible amounts of energy. For now, though, these ideas are mostly gentle dreams. We do not yet know how to build a mirror so large and precise, nor can we produce and control the amount of antimatter that would be needed, nor maintain such a laser array in space. A more explosive idea for starflight reaches back to the middle of the 20th century. In the United States, a project was proposed that imagined using nuclear devices not as weapons, but as steps on a ladder to the stars. The plan called for a spacecraft equipped with a nuclear pulse engine. Behind the main body of the ship, engineers would place a sturdy, heat-resistant plate cushioned by shock absorbers. Small nuclear charges, roughly on the scale of 1 kiloton of TNT each, would be ejected, one after another, behind the plate and detonated at carefully chosen distances. Each explosion would create a brief but powerful surge of hot plasma that slams into the backplate, pushing the spacecraft forward. The shock absorbers would smooth out the jolt, turning a series of violent pulses into a more manageable, if still rough, acceleration. In theory, by repeating this process thousands of times, the ship could be pushed to extraordinary speeds, fast enough to reach the Alpha Centauri system in about 130 years. For a crewed mission, that is still a voyage spanning generations, but it is vastly shorter than the tens of thousands of years chemical rockets would need. On paper, the idea worked. In practice, it ran into serious problems. One was environmental and ethical. Launching such a ship from Earth would mean setting off many nuclear explosions in or near our atmosphere, spreading radioactive material and violating test bans. Another was engineering. Designing a pusher plate and shock absorber system that could survive so many blasts without failing is a daunting challenge. Even if each individual explosion is not enormous by nuclear standards, their repeated hammering would test the limits of materials and design. Over time, concerns about radioactive pollution, political treaties, and practical difficulties combined to cast a long shadow over the project. In the end, the nuclear pulse propulsion concept was set aside. The work on building such an engine was halted, and the designs were left in old reports and archives. For now, they remain as an intriguing what-if in the history of our attempts to imagine ways of reaching the nearest stars. Even though some ideas for nuclear propulsion turned out to be too dangerous or impractical, that does not close the door on using nuclear energy in space. There are quieter, more controlled ways to let atomic reactions push a ship forward. One of the simplest concepts is the nuclear thermal engine. In this design, light gas, usually hydrogen, is fed through the heart of a nuclear reactor. Inside, sturdy rods made of uranium or similar fuel release heat as their atoms undergo radioactive decay. That heat is transferred to the hydrogen, which swells to very high temperatures. Once it is hot enough, the gas is released through a nozzle. As it rushes out, it pushes the spacecraft in the opposite direction, just as exhaust gases do in a chemical rocket. This kind of engine is called a solid-core nuclear thermal rocket because the reactor fuel remains in a solid structure. The comforting part is that such engines are not pure fantasy. With our current technology, they are within reach. Their efficiency, measured in how much thrust you get per kilogram of propellant, is at least about twice that of the best chemical engines we use today. In the language of engineers, the specific impulse is roughly doubled. For a mission planner, that means the choice between carrying more payload, traveling farther, or cutting travel time for a given mass of fuel. Solid core reactors do have limits. The materials that hold the fuel and form the walls of the reactor can only tolerate so much heat before they weaken and fail. For such engines, the temperature of the active zone must stay below roughly 3,000 degrees Celsius. Above that, the structure is at risk of cracking, melting, or eroding under the combined assault of heat and radiation. If we imagine pushing the temperature far higher, up towards something like 25,000 degrees Celsius, the solid structure could no longer hold its shape. The interior would break down into a cloud of red-hot radioactive plasma, more like a miniature star than a conventional reactor core. Paradoxically, letting the fuel become a gas could make the engine far more efficient. This is the idea behind a gas-core nuclear thermal rocket. In such a design, the fissioning material is not locked into solid rods. It forms a glowing, turbulent plasma at the center of a chamber. Hydrogen, or another light propellant, flows around this central fire, soaking up heat and then streaming out through a nozzle. Because the temperatures can be so much higher than in a solid core reactor, the exhaust can be much faster, and the engine's efficiency could rise by tens of times. If we could build a reliable gas core engine, it might shorten a crewed flight to Mars from many months to just a few weeks. With enough operating time, such an engine could even give a spacecraft the extra push needed to truly escape the sun's gravitational influence and head for other stars. The challenge is not a lack of imagination, but the difficulty of holding that seething cloud of plasma in place. No known normal material can withstand direct contact with such temperatures. A physical wall would simply evaporate. To make a gas core engine work, the plasma would have to be confined and shaped by extremely strong electromagnetic fields, carefully arranged so that the hot, radioactive gas never actually touches the solid walls. This is similar in spirit to magnetic confinement schemes used in experimental fusion reactors on Earth. The same kinds of technologies, superconducting magnets, advanced control systems, materials that can tolerate intense radiation, are being studied even now. Solving these problems would not only make gas core fission engines more realistic, it would also bring us closer to an even more powerful kind of propulsion: engines based on thermonuclear fusion. Fusion is the process that powers stars. Instead of splitting heavy atoms like uranium, it squeezes light atoms such as hydrogen together until they merge into heavier nuclei, releasing vast amounts of energy in the process. For space travel, fusion has several gentle advantages. It does not require heavy, rare elements. It runs on forms of hydrogen, the most common element in the universe. The energy released per unit mass of fuel is much higher than in fission. On paper, a fusion-based thruster could use its fuel thousands of times more efficiently than the chemical engines we rely on today. If such a thermonuclear engine could be built, it might push a starship to a significant fraction of light speed, at least in principle. Journeys to the nearest stars, which now look like undertakings of tens of thousands of years, might shrink to timescales of a few decades. That is still a long voyage for any individual human, but it begins to feel like something a civilization could plan around. One particularly evocative idea in this family is called the Bussard ramjet. It is a theoretical design that modifies the fusion rocket concept by adding a vast scoop at the front of the ship. In the thin interstellar medium between stars, there is still a trace of hydrogen gas, just a few atoms per cubic centimeter, spread out like dust in a cathedral. A Bussard ramjet would spread an enormous electromagnetic field ahead of itself, funneling that diffuse hydrogen inward toward its reactors. The collected gas would serve as fuel or as reaction mass for the fusion engine. In the most optimistic versions of the idea, once the spacecraft reaches a certain speed, the amount of hydrogen it can collect equals or exceeds the amount it needs to continue accelerating. At that point, the starship becomes almost self-sustaining. It no longer has to carry most of its fuel from its home system. Instead, it grazes what it needs from the space it traverses. So far, this remains a beautiful piece of theoretical work, something that lives comfortably on paper, nourished by equations and imagination. While our minds wander through these designs, our own planet has already begun to reach out in a quieter, more accidental way. For about a century, Earth has been sending structured radio signals into space. Every broadcast, every radar ping, every television transmission leaks a little energy into the sky. This expanding sphere of radio noise has already washed over dozens of nearby stellar systems. It has reached stars like Arcturus, about 37 light-years away, and Aldebaran, at roughly 65 light-years. If there are civilizations with sensitive receivers on planets there, they might have heard the faint, delayed murmur of our presence by now. Some of our signals may also have brushed past potentially habitable exoplanets, worlds such as Ross 128b or Gliese 667cc, which orbit dimmer stars but lie in regions where liquid water could exist. So far, this is more a poetic thought than a confirmed connection, but it reminds us that we are already, in a sense, announcing ourselves to the galaxy without trying very hard. Amid all the far-off possibilities, one destination stands out as the most natural first step for an interstellar voyage: the Alpha Centauri system. It is our closest stellar neighbor, and simple proximity makes it a prime candidate for the focus of early starship designs. Alpha Centauri is not a single sun, but a multiple star system with 3 known components. 2 of them, Alpha Centauri A and Alpha Centauri B, are relatively similar to our Sun and orbit each other in a slow, graceful dance. To the naked eye from Earth, they appear as a single bright point of light in the southern sky. These 2 main stars follow slightly elongated or elliptical paths around their common center of mass. One full circuit takes about 80 years. Over that time, the distance between them varies. At their farthest separation, they may be roughly 35 astronomical units apart, similar to the distance between the Sun and the outer regions of our own giant planets. At their closest, they approach to about 11.2 astronomical units, which is a bit beyond the orbit of Saturn in our system. The distance from this pair to our Sun is about 4.36 light-years, a gap that feels both small and enormous, depending on how you frame it. The more massive, larger, and brighter of the 2 is called Alpha Centauri A. It is a main sequence star, like the Sun, quietly fusing hydrogen into helium in its core. Its mass is about 108% that of our star, just a little heavier. Its radius is about 1.22 times the Sun's radius, making its disk modestly larger. In terms of surface temperature and spectral class, Alpha Centauri A is not very different from our own Sun. It is a warm, yellowish star, but because it is slightly bigger and more massive, it emits around 1.5 times as much energy. So far, astronomers have not confirmed any planets in stable orbits around Alpha Centauri A, though many have looked. However, during observations made in infrared light in the year 2021, there were hints of a planet-like object near the star. The signal is still under study, and the evidence is not yet firm enough to claim a discovery. But even that suggestion is enough to stir a quiet curiosity. Somewhere there, so close in cosmic terms, there may be a world circling a sun very much like our own. The faint hints that telescopes have picked up around Alpha Centauri suggest there might be a large planet circling there. From the early estimates, this possible world could have a mass somewhere between 9 and 35 times that of Earth. Its radius might be about 3.3 to 7 times larger than our planets. At a distance of roughly 1.1 astronomical units from its star, just a little farther out than Earth is from the Sun, it would take about 1 year to complete a full orbit. For now, all of this is just a gentle outline, not a clear portrait. The signal is weak, and the universe is noisy. Astronomers will need many more observations to know whether this planet truly exists or is just a trick of the data. Instruments like the James Webb Space Telescope or the most sensitive observatories on Earth may eventually be able to confirm or dismiss it. Even this uncertainty carries a quiet charm. The thought that a big, strange world might be circling a sun-like star only a few light years away, waiting patiently for us to be sure. The second bright member of the system, Alpha Centauri b, often called Ptolemy, is also a main sequence star, burning steadily like our own, but it is a little smaller and gentler. Its mass is about 10% less than the Sun's, and its radius is around 86% of the Sun's radius. Its surface temperature sits near 5,260 Kelvin, slightly cooler than our star, which gives its light a soft orange tint. Put together, these details mean that Ptolemy's luminosity is roughly half that of the Sunday. Still, Ptolemy is not calm in every way. For a star of its type, it emits a surprisingly large amount of energy in X-rays. Astronomers have also seen bright flares and bursts on its surface, signs of a magnetic personality that is more active than you might guess from its warm color. So far, no exoplanets have been firmly confirmed in orbit around it. Back in 2012, a team from the Geneva Observatory proposed that a small planet might be circling very close in, taking only about 12 days to go around once and being slightly smaller than Earth. That idea was based on 4 years of carefully measuring tiny shifts in the star's motion. But 3 years later, a mathematical error in the data processing was uncovered, and the apparent planetary signal dissolved. The would-be world turned out to be a phantom born of our own calculations. The third star in the family could not be more different. Proxima Centauri is a red dwarf, much smaller and cooler than the other two. Its mass is only about 12% of the Sun's, and its radius is roughly 7 times smaller. Its surface temperature is just above 3,000 Kelvin, so it shines with a deep red glow. Its total luminosity is tiny, only about 0.17% of the Sun's output, yet it is this dim little star that stands closest to us. Proxima lies about 4.25 light-years away from the Sunday. That proximity is what gave it its name, Proxima, the nearest. It is also slowly drifting closer. Calculations suggest that in about 26,700 years, it will be just a bit more than 3 light-years away. Even at that closest approach, our eyes would still not see it unaided. Its light is too faint to show itself against the background of brighter stars in our night sky. Proxima also orbits the shared center of mass of the Alpha Centauri system, but at a great distance, like a quiet outsider circling a busy town. Right now, it sits around 13,000 astronomical units from the AB pair, about 0.21 light years. Over the next 300,000 years, that separation is expected to shrink to about 4,100 astronomical units. One full orbit around the system's common center takes about 547,000 years. Human history so far occupies only a small, thin slice of one of those vast loops. Unlike its two larger siblings, Proxima Centauri is already known to host planets. Astronomers have confirmed 2 exoplanets in its system and have at least one more candidate under discussion. Observations in infrared light hint at a ring of dust as well, a band of fine material that might resemble a colder, scaled-down version of our own Kuiper Belt. Mixed into that ring could be countless small bodies, asteroids, comets, and icy fragments drifting through the red glow. The first known planet here, Proxima Centauri b, was discovered in 2016 using the radial velocity method. By tracking tiny, regular shifts in the star's spectrum, scientists could see the subtle tug of an unseen companion pulling the star first a little toward us, then a little away. In 2020, follow-up observations with extremely sensitive spectrographs on the Very Large Telescope in Chile confirmed the planet's presence. From those measurements, Proxima b appears to orbit at about 0.05 astronomical units from its star, much closer than Mercury is to the Sunday. It completes one orbit in roughly 11 Earth days. Its mass is thought to be about 10 to 20% greater than Earth's, and its radius around 1.3 times that of our planet. Computer models suggest that Proxima b receives about 1.5 times less thermal energy from its star than Earth does from the Sunday. That would put its average temperature near 234 Kelvin, roughly 39 degrees Celsius, below the freezing point of water. Under the right conditions, especially with a reasonably thick atmosphere and some greenhouse warming, there could still be regions on its surface where liquid water exists. But the picture is complicated because it orbits so close to a relatively small star. Proxima b is very likely tidally locked. That means one side of the planet permanently faces the star, basking in endless day, while the other side remains in perpetual night. Between them lies a ring of eternal twilight. A dense atmosphere, if it exists, could carry heat from the day side to the night side, smoothing out the extremes and creating a zone where conditions are less harsh. At the same time, Proxima Centauri behaves like many red dwarfs. It is active and temperamental. It frequently unleashes flares and streams of ionizing radiation over long periods. Such stellar storms can chip away at the atmospheres of planets that orbit too close, especially if those planets lack a strong magnetic field. A powerful magnetic shield around Proxima b could help protect any atmosphere it has, bending charged particles away. But based on our current understanding, the chances that the planet carries a magnetic field as robust as Earth's are considered slim. Proxima b sits in a delicate balance. It lies in a region where liquid water might be possible, yet it also lives under a star that is constantly testing the endurance of any atmosphere it could hold. In 2020, a second planet in the system was confirmed, Proxima Centauri c. This world lies much farther out, at roughly 1.5 astronomical units from the star. It takes a little more than 5 Earth years to complete its orbit. Its mass appears to be about 6 to 8 times that of Earth, but its radius remains uncertain. Depending on its size and composition, it could be a rocky super-Earth or a mini Neptune wrapped in a thick envelope of gas. Because it orbits far from a dim red star, Proxima c receives very little warmth. Its estimated equilibrium temperature is around 39 Kelvin, roughly 234 degrees Celsius below zero. That makes it an extremely cold world, most likely covered in ices or consisting largely of frozen gases. Some observations hint that Proxima c might carry a system of rings with a radius about 5 times that of Jupiter. If that is true, those rings would arc through the faint red light like a wide, thin halo, nearly invisible to human eyes but traceable by our instruments. Data from the Very Large Telescope also point to the possible presence of a third, much smaller planet, often referred to as Proxima d. If it is real, this planet would orbit at about 0.029 astronomical units from the star, with a mass near 1/4 that of Earth. Its year would last only about 5 Earth days. The estimated surface temperature could be around 360 Kelvin, or roughly 87 degrees Celsius. That is hot by our standards, but still below the temperatures that melt rock. As of now, though, Proxima d remains an open question. Its signal is faint, and additional observations are needed to decide whether it is a true world or just another illusion in the data. For more than 100 years, the Alpha Centauri system, including Proxima, has been quietly bathed in our radio noise. Ever since we started broadcasting, our signals have been spilling into space in all directions. Music, news, radar pings, old television shows, all expanding outward as a growing sphere of faint whispers. That sphere has already reached Alpha Centauri. In a sense, our neighbors there have been listening to us for decades, whether or not anyone is actually there to receive the message. Between us and them, though, lies a distance of around 40 trillion kilometers. Light needs a bit more than 4 years to cross that gap. For human spacecraft, speeds like that remain firmly in the realm of theory and imagination. Even the fastest probes we have built so far would require tens of thousands of years to bridge such a distance if they could somehow be aimed directly at Alpha Centauri and sent on their way. Still, technology creeps forward. With advanced methods of propulsion, the journey time might be reduced dramatically. From the very first days of the space age, people have drawn up plans for starships that might one day cross interstellar space. Nuclear pulse craft, ion-driven vessels, solar sails, fusion ships. Most of these designs were set aside or forgotten, left in old papers and quiet archives. But one idea continues to be discussed with unusual seriousness: the Breakthrough Starshot program. Instead of sending one large, heavy spacecraft, Breakthrough Starshot imagines launching a swarm of tiny ones. The concept calls for about 1,000 miniature probes to be sent toward Proxima Centauri sometime in the first half of this century. Each probe would be no larger than a small coin or computer chip, only a few centimeters across and weighing just a few grams. Attached to each would be an ultra-thin, extremely durable sail. These sails would not depend on sunlight alone. A powerful array of Earth-based lasers would be used to shine intense beams onto them. The light would push against the reflective surface, and each photon bouncing off would give a minuscule shove, with many, many photons hitting continuously. The small spacecraft could be accelerated to extraordinary speeds, perhaps around 20% of the speed of light. At such a velocity, they could leave the solar system in a matter of days and traverse the distance to Proxima Centauri in about 20 years. Once they reached the target system, the probes would not slow down. They would streak through the region at high speed, snapping images, measuring magnetic fields, sampling the stellar wind, and collecting what data they could during their brief passage. Then, as they sped onward into the dark, they would turn their tiny transmitters back toward home and begin sending their findings. Those signals, traveling at the speed of light, would then have their own long journey to make. After the roughly 20-year flight, it would take another 5 years or so for the first bits of information from that interstellar flyby to wash back over Earth, arriving like a faint echo from a quiet, red star we have been wondering about for so very long. When you step back from all these plans and tiny starships, the same truth keeps returning. The distances out there are staggering. Even here in our own cosmic backyard, a trip takes time. With the engines we have now, going to the moon is not instant. It still takes days and careful planning. Reaching Mars along an efficient path takes more than 6 months of quiet coasting between worlds. If we think about the legendary Voyagers, their story is even more humbling. After roughly 45 years of travel, they have only just slipped past the inner parts of the solar system. Ahead of them lie thousands of years drifting through the scattered disk and, eventually, the vast, ghostly shell we call the Oort cloud. The fastest probe we are flying at the moment, the Parker Solar Probe, is expected to reach a record speed of about 194 kilometers per second, around 2025. But that dizzying speed is only possible because it is falling deep into the sun's gravity well. That same gravity will keep it bound to our star. Parker cannot use that speed to escape the system. Instead, it is doomed to graze the sun again and again until it is finally destroyed in the star's outer layers. All of this hints at a quiet limit. Chemical rockets, the kind that rely on burning fuel and pushing hot gas out of a nozzle, seem to be approaching the end of what they can reasonably offer. They are wonderful for climbing off a planet, reaching orbit, and visiting nearby worlds, but they are poorly suited for journeys to other stars. There are alternative ideas. Nuclear pulse propulsion, where small nuclear devices push a ship forward in a series of controlled jolts, or solar sails and electric sails that let starlight and solar wind do the pushing. Each comes with serious challenges, from engineering and materials to politics and safety. Still, it is hard to imagine that these difficulties will remain unsolved forever. People are patient, and curiosity is stubborn. Even if we manage to build better engines, there is another challenge that cannot be ignored: power. Long-distance travel is not just about moving. It is about keeping a ship alive while it moves. Most spacecraft we build today are quite small and carry power sources that are reliable but weak. Many deep space probes use radioisotope batteries, where the heat from radioactive decay is turned into electricity. These steadily fade as the fuel ages. If you look back at the Voyagers, you find that almost all of their instruments have already been turned off to save power. For years now, the spacecraft themselves have been traveling mostly by inertia, coasting with only a few systems still awake. Space stations such as the International Space Station use solar panels, sometimes combined with small radioisotope generators. But much of their power goes just to keeping people alive, running air systems, keeping temperatures stable, recycling water. Electric thrusters, when present, are used only to nudge the orbit from time to time. For a long-duration crewed mission to a distant planet, or especially to another star, a ship would need far more power than this. It would have to run life support, scientific equipment, communication systems, and perhaps powerful engines, all at once, for years or decades. 99% of any journey to another star would be spent in interstellar space. Out there are no big solar panels bathed in strong sunlight, no handy fuel depots. Even the radiation from the brightest stars is faint by the time it has spread across such huge distances. It thins out into a cold drizzle of photons. That is why, if we dream seriously about traveling to other worlds, we need an energy source that is autonomous, powerful, and as close to inexhaustible as we can manage. To look for clues, it helps to turn our attention back to the universe itself. On the smallest scales, nature seems to play with forms of energy and structure we barely understand. Some of the physical processes that appear in this deep structure might, one day, hint at ways to feed a starship. To glimpse that possibility, we need to take a small detour into the strange behavior of what we used to think of as empty space. In 2017, a group of researchers from Princeton and Hong Kong built a tiny device that, at first glance, seemed to tease one of physics' most cherished rules. The mechanism was microscopic. Two thin silicon plates placed in a vacuum, separated by a distance of about 100 nanometers, a gap so small it would take thousands of them to span the width of a human hair. In that arrangement, the device was able to produce a small but measurable amount of energy that looked as if it came from nowhere. On the surface, that seems to clash with the law of conservation of energy, the rule that says you cannot get energy for free. But the story is more subtle than that. The device's behavior relies on something called the Casimir-Polder effect, usually shortened to the Casimir effect, first described in the middle of the 20th century. In simple terms, if you place two uncharged, parallel plates very close together in a vacuum, they will feel a tiny force pulling them toward each other. This force is tied to another strange feature of the quantum world, the Heisenberg uncertainty principle, which implies the existence of zero-point vacuum fluctuations. According to this picture, even a perfect vacuum is never truly empty. Pairs of virtual particles that pop into existence and then vanish, are constantly appearing everywhere in space. They live for an incredibly short time, perhaps around 10 to the power of minus 24 seconds, and then annihilate each other again, restoring the overall balance. In open space, virtual particles of many different wavelengths and energies can flicker in and out freely. Between two closely spaced plates, though, only certain wavelengths can fit in the gap. The virtual particles between the plates are restricted, while outside the plates, they are not. As a result, the density of vacuum fluctuations outside is slightly higher than inside. You can imagine it as if the vacuum between the plates has had a little extra stuff pumped out of it, creating a kind of negative pressure. The region between the plates feels like a place where the vacuum pushes less, while the outside pushes more. That mismatch creates a net force that presses the plates together. The team at Princeton and Hong Kong found a way to turn this gentle mechanical tension into a tiny electric current. The current they produced was very weak, nowhere near strong enough to power anything large. But the principle is what matters. It shows that, under the right conditions, we can extract useful energy from the restless structure of the vacuum itself. From the outside, it looks almost like energy from nothing. Yet, it still respects the deeper bookkeeping of quantum fields. Even a very low power but truly inexhaustible source of energy would be incredibly valuable. It could serve as an autonomous power supply for microprocessors and precision sensors, devices that need only a faint trickle of current but must run for decades without interruption. If something like the Voyagers had been equipped with such hypothetical vacuum batteries, their instruments might still be sending back data from the edge of interstellar space today. For deep space exploration, even tiny, immortal power sources open new paths. The Casimir effect leads to other, even more speculative ideas. One of them is called the Scharnhorst effect. Calculations suggest that if you send light through the narrow gap between Casimir plates, the speed of light in that region could be very slightly higher than the usual value of 300,000 kilometers per second. The reasoning is that with fewer vacuum fluctuations between the plates, photons have fewer chances to bump into virtual particles and are, in a sense, less hindered. We do not yet have the technology to perform a clean, convincing experiment to test this effect, and even if it is real, the change in speed would be tiny, but the mathematics behind it flows into a wider river of thought. It suggests that by shaping the quantum vacuum with strong fields and special arrangements of matter, we might be able to tweak the properties of space itself. That idea, in turn, has fed into one of the boldest concepts in modern theoretical physics, the notion of a warp drive, often called an Alcubierre bubble. Two scientists at Baylor University, Gerald Cleaver and Richard Abalzi, took the equations of quantum field theory and general relativity and combined them to examine this idea more carefully. Quantum field theory, in some versions, hints that space may have more than 3 dimensions, though the extra ones curl up to sizes too small for us to notice directly. When the researchers applied these equations to the Casimir effect and similar phenomena, they concluded that, at least on paper, it might be possible to control some of the vacuum's properties using very intense energy fields. If, in principle, you could compress space behind a hypothetical starship and stretch or thin it in front, you would create a region where space itself moves. Inside this bubble, the ship could ride along as if on a moving walkway. From the point of view of someone outside, the bubble could travel faster than light, even though the ship inside never breaks the speed limit set by relativity in its local patch. In that way, the rules of Einstein's theory are not actually violated. Nothing moves through space faster than light. Instead, space itself does the moving. It is an elegant idea, and in equations it behaves beautifully. But from the very beginning, one enormous obstacle has stood in the way: the energy bill. Early calculations suggested that to create a warp bubble large enough to hold even a modest spacecraft, you would need to manipulate unbelievable amounts of energy. Some estimates implied that an entire planet would have to be converted into radiation to form and sustain such a region of warped space, a price far beyond anything our small blue world could ever afford. If, someday, researchers learn how to scale up generators based on the Casimir effect to truly large capacities, we might be able to tap energy almost anywhere in the universe from what looks like nothing at all. Even then, the path to a fully working starship would not be simple. Space beyond Earth's comforting air is not a gentle place for human bodies. Everywhere outside our protective atmosphere, high-energy particles move through the void like invisible rain. This radiation can slice through cells, damage DNA, and seed mutations that echo into future generations. To shield against it, We can imagine thick metal walls or carefully shaped magnetic fields that curl charged particles away, just as Earth's magnetic field guides many cosmic rays toward the poles. Both approaches have trade-offs. Heavy shields are difficult and expensive to launch. Strong magnetic fields demand power and can interfere with electronics or biology in their own ways. Then, there are the smaller, sharper dangers, micrometeoroids and grains of cosmic dust. At everyday speeds, a grain of sand is harmless. At a significant fraction of light speed, even a speck becomes a tiny bullet, packing enormous kinetic energy. It can punch through metal, tear open cables, or crack delicate instruments. On an interstellar voyage lasting decades, repair options would be limited. A single unpatched hole in the wrong place could be fatal. Any true starship design has to think of its skin not just as a shell, but as a living armor that can detect, absorb, and heal. Beyond shielding and structure, a long journey with little or no support from Earth demands something even more challenging: a closed biosphere. The ship would need to carry its own small, looping world inside air that can be cleaned and renewed, water that can be filtered and reused, food that can be grown and harvested in cycles. Scientists around the globe have been exploring pieces of this puzzle for years. On the International Space Station, various plants have been grown in orbit, both as science experiments and as tiny gardens. Engineers are designing systems to recycle waste, including biological waste, turning what we used to throw away into new raw material. Yet a complete, stable ecosystem in orbit, a miniature Earth that can run on its own for decades, is still far beyond what we have. There are feedbacks to understand, microbes to manage, and countless small balances to keep. It is one thing to run a sealed habitat for months. It is another to trust one with generations. If we look out from our solar system on a galactic map, our surroundings seem sparsely populated. On the grand scale of the Milky Way, the outer edges of the local bubble, where our sun lives, are not crowded. Still, within a radius of 15 light-years, astronomers have identified around 50 stellar systems. Some hold a single star, others contain 2, 3, or more suns moving around a shared center. Altogether, there are about 65 stars in this little neighborhood. Many of them host exoplanets. Around some, there are protoplanetary disks, broad rings and clouds of gas and dust, where new worlds are still forming or slowly carving out their orbits. If we wanted to take stock of this variety, to truly understand the space just beyond our own backyard, we would need to map it star by star, system by system, as we drift outward. So, in imagination, we can let our perspective slip free of the sun a little more. We move slowly, in light-year steps, our home star shrinking behind us. After we have traveled about 6 light-years, we reach our first major stop, a small red dwarf cataloged as GJ 699, more commonly known as Barnard's Star. Barnard's Star is modest in every way except motion. Against the background of more distant stars, it glides noticeably from year to year. Over about 180 years, it appears to cross the width of our moon's disk in the sky. This high proper motion is due partly to its relative closeness and partly to its true speed through space. Barnard's Star is moving toward the solar system at slightly more than 100 kilometers per second. In roughly 10,000 years, it is expected to become our closest stellar neighbor, closing in to about 3.8 light-years from the Sunday. Even then, it will remain invisible to the naked eye. Red dwarfs are frugal with their light, and Barnard's star is no exception. Its mass is only about 17% of the Sun's, and its radius is roughly 6 times smaller. Like other stars of its class, it is cool by stellar standards, with a surface temperature of around 3,134 Kelvin, just under 2,900 degrees Celsius. Its luminosity is astonishingly low, about 1/2,300th that of our Sunday. To shine like the sun, you would need more than 2,000 Barnard stars burning together. In 2018, astronomers published the results of a 20-year campaign carefully tracking the star's motion. Hidden in those data was a subtle, repeating wobble that may hint at a companion. Their calculations suggest a cold, super-Earth in orbit there, with a minimum mass of about 3.2 times that of Earth. This planet, called GJ 699b, appears to circle its star at a distance of about 0.4 astronomical units and take roughly 233 days to complete one orbit. Because the planet's path does not carry it directly between the star and Earth, it does not transit the stellar disk from our point of view. That makes it difficult to study with the spectral methods we often use to probe exoplanet atmospheres. Instead, we lean heavily on models and indirect clues. Barnard's star is very dim, so its planet receives 50 times less energy from its star than Earth receives from the Sunday. Under simple assumptions, the surface temperature of such a world would be around 105 Kelvin, about 168 degrees Celsius below freezing. On the surface, it would be a frozen, lightless realm, but there is room for more nuanced possibilities. Tidal forces and the slow decay of radioactive elements in the planet's interior might release enough heat to maintain a subsurface ocean beneath an icy shell, as is thought to happen on moons like Europa or Enceladus in our own system. If such an ocean exists, it could have been stable for a very long time. Barnard's star appears to be one of the oldest known stars in our neighborhood, with an age estimated at over 10 billion years, a significant fraction of the age of the universe, and only partway through its own long lifespan. If any life ever found a foothold in a hidden sea there, it would have had aeons to change and flourish in ways we can only guess at. Because of its closeness, its age, and its motion toward us, Barnard's star sits high on many lists of attractive targets for a future interstellar probe. It is a quiet, ancient ember, close enough that a patient starship might plausibly visit it within a few human generations. If we turn our gaze in another direction, across the sun to the opposite side of the sky, we find almost the mirror image of Barnard's dim red point, Sirius, the brightest star in our night. Sirius lies about 8.6 light-years from Earth, close by on galactic scales, but much farther than Barnard's star at its future closest pass. To our eyes, Sirius looks like a single, piercingly bright point of bluish-white light. Closer attention, however, reveals that this brilliance comes from a pair. Sirius is a binary star system. The two components are currently near the widest part of their orbit around their common center of mass, separated by about 30 astronomical units, roughly the distance from the Sun to Neptune. The main star, Sirius A, is a bright blue-white object with a mass about twice that of the Sunday. Its diameter is about 70% larger than the Sun's. Its surface temperature climbs to around 10,000 Kelvin. With that hotter surface and greater area, Sirius A radiates roughly 25 times more energy than our star. It is this lavish output that makes it so dazzling in our sky. Its companion, Sirius B, is almost lost in the glare. It is a white dwarf, a stellar remnant, left behind when a star like the Sun runs out of fuel. Sirius B's radius is only about 6,000 kilometers, not much smaller than Earth's diameter, yet its mass is very close to that of the Sunday. Its surface temperature is fierce, around 25,000 Kelvin, but its tiny size means its total luminosity is low. Seen on its own, it would be about 1,000 times dimmer than Sirius A. Despite long and careful searches, astronomers have not found clear signs of planets in the Sirius system. One reason may be its relative youth. Another may lie in geometry. If potential planets do not pass directly between the stars and Earth, the common transit method will not reveal them. There is also a deeper possibility. Models suggest that Sirius B exhausted its nuclear fuel around 120 million years ago. As it aged, it would have swelled into a red giant, expanding and shedding its outer layers in a dramatic phase of its life. That evolution could have destroyed or disrupted much of the original protoplanetary disk of gas and dust. In that scenario, any forming planets might have been stripped of material or ejected. The gas and dust that once circled the young binary like a cradle could have been blasted away into surrounding space, leaving little chance for stable, long-lived worlds to settle into orderly orbits. What remains today is a bright, still young main sequence star and its compact, dense, cooling companion, locked together in a slow dance. Both stars move around their shared center in moderately elongated ellipses, completing one full orbit every 50 years. Over the next 60,000 years, the Sirius system is expected to drift a little closer to Earth, making the star appear even brighter in our night sky. At its closest approach, the distance between us will shrink to about 7.5 light years. After that, the system will begin a slow retreat, growing fainter over hundreds of thousands of years. For roughly the next 660 million years, this approach and recession will play out, and Sirius A will continue to blaze proudly in our heavens. Eventually, though, it too will reach the end of its stable life. When that time comes, Sirius A is expected to swell into a red giant, dramatically increasing its brightness. For a brief span, a massive flare in luminosity will make it shine thousands of times more brightly than it does now. Then, over a matter of months, it will cast off its outer layers, fade, and collapse into a compact remnant. In our sky, the once brilliant beacon will dim past easy recognition and at last vanish from the sky forever. If we drift outward from Sirius, away from the harsh wash of its ultraviolet light and the steady push of its stellar wind, we can imagine our path bending gently again. Our course swings back past the familiar plane of the solar system, not to stop, but to use its gravity and orientation as a quiet turning point. From there, our line of travel extends toward a small, faint star about 14 light years away, Wolf 1061. In star catalogs, it carries several names, but Wolf 1061 is the one that tends to linger. It is a red dwarf, modest in size, with a radius of roughly 30% of the Sun's and a mass about 4 times smaller than that of our star. Its surface temperature is around 3,272 Kelvin, about 3,000 degrees Celsius, so it glows with a deep, warm red. Like other stars of this class, it is extremely dim in visible light. Its luminosity is only around 1% of the Sun's, so you cannot see it with your naked eye from Earth, no matter how clear and dark the night. What makes Wolf 1061 special is not its brightness, but its company. For such a small star, it hosts a surprisingly rich and varied set of planets. Astronomers have found at least 3 rocky exoplanets in orbit there. They are similar to Earth in basic composition, built mostly of rock and metal, but the conditions on each are very different. The innermost world, Wolf 1061b, hugs its star tightly. It orbits at a distance of only about 0.038 astronomical units from the center of the system and completes a full orbit in roughly 5 days. Its mass falls somewhere between 1.5 and 2 Earth masses, and its radius is about 20% larger than Earth's. At such a close distance, the planet is almost certainly tidally locked, showing the same face to its star at all times, like the moon does to Earth. On the permanent day side, the temperature is expected to be extreme. Flares and streams of charged particles from the nearby star wash across it constantly. Under such conditions, any atmosphere the planet might once have had is likely stripped away, especially on the star-facing side. In our quiet mental map of possible homes, Wolf 1061b becomes a place to study rather than a place to settle. A rocky ember baked too hard and too close to its parent. The second planet, Wolf 1061c, sits farther out at a distance of about 0.089 astronomical units. It takes around 18 days to circle the star and lies within the star's habitable zone, the region where temperatures could, under the right circumstances, allow liquid water to exist on a planetary surface. It is more massive than Earth, about 3 to 4 times as heavy, and belongs to the family we call super-Earths. Observations suggest a radius around 1.6 times Earth's, and surface gravity roughly 60% higher than what we feel here. Walking there, if you could, each step would feel heavier, as if carrying an unseen pack on your shoulders. Wolf 1061c receives noticeably less energy from its star than Earth does from the sun, so its equilibrium temperature, what you would calculate for a bare rock with no atmosphere, is lower. Numbers place it near 223 Kelvin, about 50 degrees Celsius below freezing, only a little warmer than the average on Mars. But planets are rarely bare, simple rocks with day-night cycles, seasons, and especially with a sufficiently dense atmosphere. Real surface temperatures could vary widely. A thick blanket of greenhouse gases could trap heat, raising the average and allowing liquid water to pool in oceans or lakes. In that case, the world's climate might slide toward conditions that, while different from Earth's, are still gentle enough for life as we know it to find footholds. Among all the potentially habitable exoplanets we have cataloged so far, Wolf 1061c is one of the closest to us, ranking near the top of the list in terms of distance. That makes it an especially tempting target for future telescopes and, in the far future, perhaps even for robotic probes. The third known planet, Wolf 1061d, moves along a more stretched out, elongated path. At its farthest point, or a pastern, it swings out to about 0.73 astronomical units from the star. At its closest approach, or periastron, it comes in to about 0.21 astronomical units. One full orbit takes about 217 Earth days. Its mass is estimated at around 7.7 times that of Earth. If Wolf 1061d is mostly rock, like a scaled-up Earth, its radius might be about 1.7 times ours. If, instead, it is more like a mini Neptune, swathed in a thick, layered atmosphere, its diameter would probably be at least 2.2 times Earth's. In either case, its path never quite carries it into the star's habitable zone. It remains too cold, too far for surface liquid water under normal assumptions. Even so, it offers scientists a valuable case for understanding how planets form and evolve around small stars, and how orbits change over time. For planetary science, uninhabitable does not mean uninteresting. The Wolf 1061 system is more than just a cluster of worlds. Its location in space is intriguing too. The star sits near the outer edge of a region called the local interstellar cloud. This is not a cloud in the sense of something fluffy and visible, but a vast volume of hot, extremely rarefied hydrogen gas. Its temperature is estimated at about 7,000 Kelvin, but its density is incredibly low on average, only about 0.3 atoms in each cubic centimeter of space. That is roughly half the typical density of gas in the Milky Way's interstellar medium. For roughly the last 10,000 years, the solar system has been moving through this local interstellar cloud. The cloud itself is about 30 light-years across, but our system lies close to its edge. Alpha Centauri, for example, already sits in a neighboring region, sometimes called the G cloud. If our current understanding is correct, the Sun will spend only about another 2,000 years inside the local cloud, before drifting into an even thinner, hotter area beyond. The local interstellar cloud is thought to have formed where two huge bubbles of hot gas in the galaxy collided and overlapped, stirring and compressing their edges. Like everything in space, the cloud has its own motion, its own direction and pace, which happens to be tilted relative to the Sun's path. It also carries a magnetic field and background radiation. From the ground, none of this is obvious. The energies involved are high, but the gas is so thin that, for life on Earth, the cloud poses no direct danger. The solar wind creates a protective bubble, the heliosphere around our system, deflecting most incoming charged particles. Those that do manage to slip through are mostly absorbed and slowed deep in our atmosphere, turning into harmless traces of heat. Even so, the cloud leaves fingerprints. In Antarctic ice cores, scientists have found traces of an isotope called iron 60, sometimes poetically nicknamed interstellar iron. This isotope is not produced in large amounts on Earth. It is thought to have arrived from outside the solar system, possibly carried by dust, grains, or gas from supernovae, and from regions like the local interstellar cloud. Tiny signatures like this remind us that our planet is not sealed off, but gently bathed in the wider galaxy's history. If we keep following our imagined route outward, we soon come to a star with a personality very different from the ancient, slow-burning red dwarfs we have just visited. This one is called AP Columbae, or AP Columba, and it lies about 27.4 light-years from Earth. What draws attention to it first is its youth. AP Columbae is only about 40 million years old. When it was born, the age of dinosaurs on Earth had already ended tens of millions of years earlier. In stellar terms, this star is still in its cosmic childhood. Even more striking is that AP Columbae was not born where we see it now. By tracing its motion backward, astronomers have concluded that it likely formed about 450 light-years away, in a completely different part of the galaxy. Young stars usually remain near their birth clusters for a long time, hundreds of millions of years, moving with their siblings through space. AP Columbae is an exception. a runaway child. When researchers reconstruct its past path, they find that it probably once belonged to an open cluster known as IC 2391, a loose gathering of about 30 stars that share a common origin and direction. At some point, a few million years ago, one of the cluster's massive members ended its life in a supernova. The explosion sent shockwaves through the surrounding gas and stars. In the delicate gravitational balance of the cluster, that sudden loss and jolt would have acted like a kick. AP Columbae appears to have received enough of that push to send it flying out of its birthplace, setting it on the solitary journey that brought it to its current location. Today, AP Columbae is a small red dwarf with a mass of only about 13% that of the Sunday, yet it behaves oddly when compared with other stars of similar mass. It seems to emit around 4 times more energy than any known star with the same basic parameters. Its radius, too, is roughly twice as large as standard models of stellar structure would predict for a red dwarf of its mass and age. On paper, it looks too bright and too big for what we think it should be. One clue to this puzzle comes from its chemical fingerprint. When astronomers examine its light with sensitive spectrographs, they find unusually strong lines from lithium in its spectrum. Lithium is abundant in the gas clouds that collapse to form new stars. But once thermonuclear fusion begins in a star's core, lithium is quickly destroyed. In most fully settled stars, especially older ones, very little lithium remains. The high lithium content in AP Columbae tells us that it is still very young and not yet in the calm main sequence phase where stars spend most of their lifetimes. Because it is so young, AP Columbae is restless. Its interior is still adjusting, and its magnetic fields are active and tangled. The star is prone to flares and violent outbursts, ejecting streams of stellar material into space. During these events, its luminosity can spike by up to a factor of 10 for short periods. If there were mature planets close by, such tantrums would be dangerous, likely stripping atmospheres and bathing surfaces in harmful ultraviolet and high-energy radiation. Observations so far show no large planets within about 4.5 astronomical units of the star. That is not surprising. At only 40 million years old, the system may simply not have had enough time to assemble fully formed, stable planets, at least not in inner orbits. Dust and gas might still be coalescing, and smaller bodies might still be colliding and merging. AP Columbae, then, is not so much a cradle for life as it is a lab for physics. By watching it, astronomers can test their ideas about how young stars behave, how they shine, spin, flare, and shed material in their earliest stages. It is a living snapshot of early stellar evolution, a reminder that every calm, steady star we see in the sky once passed through a stormy, oversized youth of its own. As we move our thoughts away from the wild, flaring youth of AP Columbae, it is worth remembering that not every star is so dramatic, and not every star carries worlds. Some shine alone in the dark. Others host just a single planet, quietly circling. Our next imagined stop is around one of these quieter suns, an orange dwarf, often listed as Gliese 370, about 37 light-years from Earth. In 2011, astronomers detected a single exoplanet around this star, now known as Gliese 370b. They found it using the radial velocity method. watching for the tiny rhythmic wobble in the star's motion caused by a planet's gentle pull. From those measurements, the planet's mass appears to be about 3 to 4 times that of Earth. Based on what we know about how such worlds form, Gliese 370b is most likely rocky rather than a gas giant, a solid planet with a radius perhaps 30% larger than Earth's. Under those conditions, the surface gravity would be stronger than we are used to, at least 40% higher, so each step would feel as if an invisible hand were pressing you slightly down. Gliese 370b orbits its star at a distance of about 0.26 astronomical units and takes around 54.4 Earth days to complete a year. That places it in the habitable zone for an orange dwarf like its host. If the reflectivity, its albedo, is similar to Earth's, models suggest an average surface temperature of roughly 25 degrees Celsius, a few degrees warmer than our own global average. Because it orbits at a comfortable distance and not in a tight, close-in path, it is unlikely to be tidally locked. Instead, it probably spins, giving it a normal day-night cycle. That spin would help spread heat more evenly around the globe, smoothing out some of the extremes between day and night and contributing to a milder overall climate. Higher gravity would tend to pull landscapes down, rounding off mountains more quickly over geological timescales, combined with abundant liquid water that could lead to wide, shallow seas, broad continental shelves, and long coastlines where land and ocean blend gently. For a long time, such sunlit, warm, shallow seas have been considered some of the most welcoming environments for the origin and support of life. It is easy to picture an ocean world there, with low rolling waves under an orange-tinted sky. When it was first announced, Gliese 370b was often highlighted as one of the most promising exoplanets for potential biological life. Later studies, however, softened that optimism a little. Updated models suggest that the planet's atmosphere might be quite dense with a strong greenhouse effect. That would trap more heat, raising the actual surface temperature above the simple 25-degree estimate. Even in the more pessimistic scenarios, though, the average temperature may not exceed about 78 degrees Celsius. That is hot, comparable to some of Earth's hottest springs and vents, but still within a range where liquid water can exist and where heat-loving life, as we know it from our own planet's early Archean era, could in principle survive. For now, Gliese 370b remains a very interesting candidate, a world that invites continued observation and more precise measurements. If we pause here and look back, we realize that in this thought journey, we have already traveled more than 50 light-years from the solar system. Within such a radius, there are over 1,000 stars, most of them solitary, some in pairs, and a few in more elaborate arrangements. One of the most striking examples of a complex stellar family is Castor, a system of 6 stars woven together by gravity. Castor sits about 50 light-years from Earth and shines in our sky as a single bright point, the second brightest object in the constellation Gemini, and the 23rd brightest star in the night. People have been watching it since ancient times, long before anyone suspected that the one star was actually 6. Because it has so many members, Castor's structure is intricate. The 2 brightest components, Castor A and Castor B, are bluish-white stars, somewhat reminiscent of Sirius in color and character. Each of them has a red dwarf companion in a relatively tight orbit, forming two close binary systems. The distance between the centers of mass of these two binaries is about 110 astronomical units, and they take roughly 445 years to complete one orbit around each other. Farther out, at a distance of about 600 astronomical units from this central pair, lies another compact binary, two red dwarfs, very similar to each other. Each of these has a mass of about 60% that of the Sun, and a surface temperature near 3,900 Kelvin. They are so close together that they whirl around one another in less than 20 hours, locked in a rapid mutual dance. This close red dwarf pair, sometimes designated Castor C, orbits around the overall system's center of mass in a very elongated orbit, taking on the order of 14,000 years for one full loop. So far, no exoplanets have been firmly confirmed anywhere in the Castor system. But if planets do exist there, theory suggests they are most likely to be found around the less massive, quieter red dwarfs in the outer pair. In 2018, astronomers detected subtle variations in the orbital period of Castor C. One possible explanation is the presence of a brown dwarf nearby, roughly 49 times the mass of Jupiter, orbiting at about 14 astronomical units and taking about 54 years to go around once. It is also quite possible that, like many red dwarfs, Castor C could host rocky planets in close-in orbits, still hidden from our instruments. If such a planet exists, the sky from its surface would be like nothing we see from Earth. On one side of the horizon, two crimson stars, its immediate hosts, might circle one another endlessly, always in motion, painting the sky with constant, slow arcs. On the other side, the soft twilight would be gently filled by the combined light of Castor A and B, each of them hundreds of times brighter than our full moon. The planet would live in a sky of perpetual interplay, nearby red suns and distant blue-white lanterns sharing the same celestial dome. For now, this is only a quiet thought. Our telescopes are not yet able to prove such a world exists, but the physics does not forbid it. All of the stars we have wandered past in this imagined tour, from our Sun and its neighbors out past Sirius, Wolf 1061, AP Columbae, Gliese 370, and Castor, sit within a larger structure about 300 light-years across. This region is known as the local bubble. It holds not just thousands of stars, but also several significant gas structures, including the local interstellar cloud we met earlier. The local bubble itself is thought to have formed through a chain of supernova explosions that occurred between 10 and 15 million years ago. Each explosion blasted hot gas into space. Together, they carved out a vast cavity in the interstellar medium. The gas filling this bubble is extremely hot, around 1 million Kelvin, but also extremely thin, with a density about 10 times lower than the galactic average. Because it is so hot and ionized, this gas emits X-rays, bathing the interior of the bubble in a soft, high-energy glow invisible to our eyes. Our planet sits inside this bubble, but we are not left exposed. The Sun's magnetic field, carried outward by the solar wind, and Earth's own magnetic field and atmosphere act as layered shields. Most of the potentially harmful radiation from the hot gas is deflected or absorbed long before it reaches the surface. We walk under blue skies and watch ordinary weather, unaware that on much larger scales, our home is cruising through a kind of gentle, hot fog. The local bubble does not exist in isolation. It is bordered by other, similar cavities in the interstellar medium. In the general direction of the Sun's motion lies another extended structure, sometimes called Bubble 1, formed by supernovae in the region near Antares and its surrounding associations. For a long time, our bubble and this neighbor have been pressing against each other, their edges interacting. Where they meet, gas can be compressed into denser filaments and clouds, seeding new regions of star formation along the boundary. The center of this neighboring bubble is roughly 500 light-years away. In a few tens of millions of years, if the galaxy's motions stay roughly as we model them, the solar system will reach the outer margins of the local bubble and then slide gradually into contact with new structures, new pockets of hot gas, new patterns of density and field. Through all of this, one thing remains constant: the quiet push of human curiosity. Across thousands of years, people have looked up and wondered what lies beyond the familiar patterns of stars. That wondering has turned into questions, equations, sketches of machines, and eventually into rockets, satellites, and telescopes. Technology grows step by small step. Ideas that would have sounded like fantasy just a few decades ago. Giant orbiting observatories, probes visiting the outer planets, detailed maps of exoplanets have become part of our ordinary scientific life. Today, we maintain a ring of satellites around our world, build enormous observatories on high mountaintops and in cold deserts, and place telescopes in space to escape the blurring effects of our atmosphere. Each new tool gives us a slightly clearer view of the universe, and each view raises fresh questions. Somewhere in that ongoing conversation between instruments and imagination, between data and daydream, there may come a moment when a starship, large or small, sets out for one of the nearby suns we have quietly traced in thought tonight. And if that happens, it will be because the same simple impulse that makes you look at the sky and wonder never quite went away.